It is shown in this video that the mass-energy relationship E equals mc² is inherent to classical mechanics. Notably, the same equation used here to demonstrate that fact is used also by Einstein in his failed attempt to derive E equals mc². It is indeed a failed attempt because the theory itself Einstein uses for this purpose is based on internal contradictions. Thus, Einstein's relativity derives two distinctly different laws of motion for one body in one system. It would have been enough for Einstein to apply just the first postulate to the first set of equations in part 10 of his 1905 paper to represent them in the moving system and vice versa. However, then, a purely trivial solution would have been the result, and there would have been no discovery at all, as is really the case. In his desire to make a discovery at any rate, Einstein redundantly uses Lorentz transformations for such representation, and as a result, ends up deriving two distinctly different expressions for the law of motion of one and the same body in one and the same system. It's an indisputable absolute truth that a body in the stationary system cannot obey at the same time two completely different laws of motion. And therefore, Einstein's relativity fails fatally right at this point, prior to any further attempts to justify it, experimentally or otherwise. It is an absolute truth that one body in one single system obeys only one single law of motion at a time. The law in question, which we would analyze in this video, is the so-called Newton's second law, which is the force applied on a body is equal to the mass of the body times its acceleration. Now, this law is usually referred to as a law of motion, but in fact it is a law of rest. Consider that according to Newton's third law, at the moment a body is acted upon by another body, it experiences a force which invokes a counterforce equal in magnitude but opposite in direction. Thus, if the force is F equals ma, then according to Newton's third law, a counterforce F star will be invoked equal in magnitude but opposing the first force. So if we sum up these two forces, we'll have F plus F star equals ma minus ma equal to 0. Now, of course, we can replace here ma by F. Now further, in order to have motion, we have to have a real displacement x. the body must have moved in space at a certain distance after the impact. So we will have F minus ma times x equals 0. Now, if this is true, then it means that a distance x will be traveled by the body by spending no work, which is impossible. This is non-physical. And so there must be something more than this F that acts on the body, causing not only effect in time, affecting time as we saw here, the acting force creating a counter force, an inertial force minus ma, but also an effect in space. Now, to understand this, we have to realize that when a real displacement occurs, in fact, a change of velocity occurs, a velocity of the body occurs, takes place. So in order for this work not to be 0, we must write F real, there must be some force greater than F minus ma times the displacement. And now this will be equal to the kinetic energy of the body, whereby v is the velocity at the end of the displacement, velocity of the body at the end of the displacement. We want to explore now the concept of motion from the most basic principles, avoiding conjectures and models and so on, basing our ruminations in our discussion on absolute truths. Absolute truths in physics are, for instance, the definitions of velocity, v equals dx dt, and acceleration, dv dt. These are equalities that cannot be disputed. And we will see now where they will lead us, what conclusions we will arrive at based on these absolute truths. So let's express dt from the definition of velocity, and the same dt from the definition of acceleration. Now, of course, these two equations give the same value for dt, and we can write dx over v equals dv over a, or a dx equals f equals v dv. Now we can integrate both parts of this equality. Integral from 0 to x, a dx equals to integral from 0 to v of v dv, which is in fact 1/2 dv squared. Now we will be interested in the motion of a free body under the action of a constant force. Therefore, the acceleration A will be constant. Also, this 1/2 is constant and so forth. So we may write A 0 to x dx is equal to 1/2 integral 0 to v dv squared, which will obviously be equal to ax from 0 to x, which is equal to 1/2 of v squared from 0 to v, evaluated from 0 to v, which will obviously give us ax equal to 1/2 v squared, or better yet, 2 times ax v squared. Now this equality, this relationship between velocity, acceleration, and the spatial coordinate x, distance x, is something inevitable. We derived it based on absolute truths. Therefore, this equality cannot be disputed on any grounds. This is an absolute truth as well. Now, from this absolute truth here, we conclude that there cannot be change of displacement. There cannot be change of position of a body, of this free body, under the action of a constant force, without changing a velocity in the course of this displacement. So velocity will be 0 only when the displacement x is 0. So it's an absolute truth that when under the action of a constant force, a free body exhibits a displacement, this body must necessarily, mandatorily, change its velocity. That's another absolute truth which we have to remember and we have to take into account in our discussion. Now let's get back to the equation which will give us the expression for the real force F sub real. So the force, when we open the brackets here, the parentheses, we will have F real will be equal to ma plus mv squared over 2x. Now this term makes all the difference. This is the term which expresses the effect in space of the force applied to the body. Now if we revert to expressing this equality in terms of energy, then we'll have F real x ma x plus mv squared over 2. Before proceeding, we'll show now that the most general equations, the Hamilton's equations, are in fact equations of rest, although the modern physics considers them to be equations of motion. Now, the Hamilton's equations are as follows. Partial dH, where H is the total energy of the system, dP sub I, this is partial dH dP sub I, is equal, according to these equations, to dQi, where dQ sub I, Q sub I is a generalized coordinate, while P sub I is a generalized momentum. So it is dQ sub I dt. And the other equation is partial dH dQi equals minus dPi over dt. Now, if conservation of energy is obeyed, then the total energy H, which consists of the kinetic energy plus the potential energy, must be constant. But if H is constant, then this equality, this is equal to 0, as well as this one. But then if we have dq dt and dpi dt equal to 0, then the generalized coordinate q sub I must be a constant, and the generalized momentum p sub I must also be a constant, which means nothing other than that the velocity of the system is 0. In other words, the system is at rest. So Hamilton's equations, the most general equations in mechanics, in fact express the state of rest, not the state of motion, as they're supposed to. This problem propagates further in quantum mechanics because Hamilton's equations are at the basis of constructing quantum mechanics operators. So this is a major problem, but we will deal with the problems of quantum mechanics in another video. For now, let's go back and analyze the equation which we just derived, namely this energy which which consists of the effect in time and effect in space. Now we can easily see that when the velocity is close to 0, this term is 0. So it may be neglected. And we get the known form of the Newton's second law. This means that, as was already said, Newton's law of motion in the known form applies only to velocities close to zero, practically zero. This is Newton's second law is a law of rest, despite the fact that it's called law of motion. Now we will discuss the equation of the real force F real, which we just derived. So F real equals ma plus mv² over 2x. This equation is not some whimsical, frivolous equation which we just want to be written this way, but emerges, as we saw, from the absolute truths of physics. Now, this equation for F real reduces to the usually known Newton's second law, F equals ma, when the velocity v is practically zero. As we saw, Newton's second law is a law of rest, despite the fact that it is called a law of motion. So at zero velocity, we have F equals ma. At intermediate velocities, where none of these two terms on the right side of the equality sign can be neglected, we observe the following. Now, because of the equality v² equals twice ax, which is an absolute equality. This equality was derived from the absolute truths of physics, from the definitions of velocity and acceleration. So based on this equality, we observe that the two terms are equal to each other. Indeed, if we substitute v² in the second term, we'll have m 2ax over 2x, where the 2 and the x cancel out, and we get ma. So F real is equal to ma plus ma, which is in fact the force F in the usual sense, in the sense which force is usually observed, plus F, the same F, and we get F real is equal to 2 times the usual F, which we know from Newton's second law. This is for intermediate velocities. Now for high velocities, we observe the following. Now, at high velocities, the acceleration being constant will become more and more negligible in comparison with the ever-increasing velocity. Of course, m is a constant too, and we can take it here as, just for simplicity, as unity. So this whole product ma will become more and more negligible as the velocity increases. And it's certain velocities, this term can be neglected. Now, ma, however, is equal to mv squared over 2x. We just saw that. So this second term can also be neglected at high velocities, which means that at high velocities, the concept of force loses meaning. Motion cannot be described, cannot be characterized anymore by force. If we write this equation in its energy form as F real x equals max plus mv squared over 2, we see that the second term after the equality cannot be neglected. And so is the first term, because these two terms, as we saw, due to the basic equation of classical physics, v squared equals 2 times ax. These two terms, because of this, v squared equals 2 times ax, are equal. So we may write f real x equals mv squared over 2 plus mv squared over 2. That is f real x is equal to mv squared. And now we remember that at these high velocities, velocity is devoid of its acceleration. That is, velocity is constant at high velocities. And instead of mv squared, we can write mc squared, where c is a constant. And we also notice that f real times x is work done to transport the body across a distance x by the force f real. And instead of the work, we can write the energy needed to do this work. So we write E, energy, equals mc squared. And this is how the mass-energy relationship arrives in classical physics, how it is inherent in classical physics, evolving from the absolute truths of classical physics. Now, briefly again, the equation for the real force, F sub real, reduces to the equation F equals ma, known from Newton's second law, when the velocity of the body is low, is practically zero. Now this is the initial moment of application of the force, and this equation expressing Newton's second law in fact signifies the effect of force in time. This is F equals m dv dt, which is dmv over dt, and that is the change of momentum per unit time. This equation, Newton's second law, shows the effect of force in time. However, when the free body, initially at rest, really finds itself in motion under the action of the constant force, there's this second term which begins to play a role, and which is not present in the known form of Newton's second law. The second term is neglected in contemporary physics, but it must be considered, as was seen. This second term expresses the effect of force in space. It shows energy per unit displacement in space. And as we saw, because of the absolute equality, v² equals 2 times ax, these two terms are equal to each other. Therefore, we have f sub real is equal to 2 times ma. From this equation, we see that acceleration A is intimately connected with the force applied on the free body. And it is constant in this discussion. So, if we draw the line of the dependence of velocity over time, the acceleration will be the slope of this line. Now, what's interesting here is that acceleration being constant will become more and more negligible in value in comparison to the velocity, ever increasing velocity. And at certain velocities, acceleration can be neglected practically. We can also observe the dependence of v over x, this parabola. And we see here also that velocity doesn't change in a straight line, but it tends towards a plateau. It doesn't reach a plateau, but it tends towards a plateau. And it will not reach a plateau if we consider acceleration playing a role. However, as the motion progresses, velocity takes over more and more, and the quantity that characterizes the body, the motion of the body, will not be the force anymore at high velocities, but will be taken over by the kinetic energy of the body. The energy of the body will be now the characteristic quantity for the motion of that body at these high velocities. And at these high velocities, because acceleration can be practically neglected, the velocity will become practically constant. At these high velocities, acceleration loses more and more significance, and therefore force loses significance. Therefore, we must express the motion of the body in terms of energy quantities, because energy takes over. This is the significant quantity that already governs motion of the body at high velocities. So we'll have to rewrite the equation for f sub real as real x equals max plus mv² over 2. But as was said, for high velocities, acceleration loses more and more meaning, and the velocity of the body tends towards a constant velocity, c. And because these two terms are equal to each other, we can write f real x equals mc², and if this is energy, this is work done to transport the body across the displacement x. And to do this work, we need to spend energy, E equals mc². And of course, we have to recall that this x is in fact, it's really a displacement. This is a delta, because we start from 0 to x. And this is a delta x. So this is a change of position in space. This was the reasoning behind the necessity to correct the expression of Newton's second law. If this expression is to describe motion of a body under the action of a force, as seen, a term is to be added which reflects the effect of force in space. Now, for low velocities, other than velocity 0, where F equals ma, Newton's second law is valid, for low velocities, both terms are in effect ma and mv² over 2x. However, at high velocities, as the velocity grows, gets higher and higher, the force loses meaning, and the energy expression takes an effect, from which, in a very natural way, the mass energy relationship evolves.